Hi everyone, this is a video to describe how to solve problems related to rate laws. And rate laws are going to be equations that we're going to write that describe how fast a reaction proceeds. So everything in the current unit is about how quickly something happens. And so we're going to go from, we've been kind of describing things qualitatively, and now we're going to move towards describing them quantitatively, meaning with numbers and equations. So the way you do this is you conduct an experiment. So you have to conduct more than one experiment. And then you can see over here that we have 3 experiments, 1, 2, 3. And in the columns here, we're going to see that anytime this symbol here with the brackets, CL2, close brackets, and this little 0 down here, we're going to read this as the concentration of Cl2 initially. So that little 0 here refers to at time equals 0. So in other words, when the experiment first begins, the initial concentration. So this whole column here is going to be of initial concentration of Cl2. This column is going to be the initial concentration of O2. And then the rate is measured, and we've put it in this column here. I forgot to mention, we've given we know the reaction equation, and I've given it to you, and I've balanced it. Notice that the ratio of 2 to 1 here does not play a role. It plays an indirect role here. So for now, we're going to ignore those stoichiometric coefficients because they're not going to play an important role just yet. We'll come back to that later on. So every rate law has a certain form. The rate law is always in the form of rate equals a constant that we're going to have to solve for times the concentration of each of the reactants, and each reactant is raised to a different power. So we have 2 reactants. That means we have 2 terms in our rate law, and these terms are raised to these powers that are referred to as orders. I wish that these were referred to as something else, but this is the order with respect to Cl2, and B is going to be the order with respect to O2, and it's just the power that we find when we go through and do the math that we're about to do, all right? So order has nothing to do with the order in which things occur, first, second, third. It has nothing to do with that. Nothing to do with that. It's just a stupid name for these exponents here, all right? So the way we're going to do this is we're going to take our first 2 experiments here, experiment 1 and experiment 2, and we're going to plug these into our generic rate law. This first one here, the first step here is to write this generic rate law containing both reactants, all right? And so we're going to plug in our first experiment. The rate is 1.8 times 10 to the minus 4 molar per minute. That's going to be equal to this rate constant that we're not doing anything with just yet. And our initial situation was 0.1 to this A power, the order with respect to Cl2, and then times 0.10 with respect to the B power. And so all I'm doing here is taking this first experiment here, and I'm just plugging it in to my generic rate law equation, all right? Now I'm going to repeat the same thing for the second one, and I'm going to write it directly below here for a reason. So I'm going to plug in 3.6 times 10 to the minus 4 molar per minute equals K times 0.10 molar to the A times 0.20 molar to the B. All right, now what we're going to do is we're going to do a sneaky math trick. We're going to divide this top equation by the bottom one. And what's going to happen here is that a lot of things are going to cancel out, and this is going to make it a lot easier. So for example, our units here cancel out, so that's good. Our rate constants, K, cancel out. 0.1 to the A, we have one of those up in the numerator, we have one of them in the denominator, those cancel out. So what we're left with is on the left-hand side, if you divide these two, you'll find that that's equal to 1/2, because 3.6 is just twice 1.8. That's going to be equal to 0.1 to the B over 0.2 to the B And one of the little things you may have forgotten from Algebra 1, way back whenever you had it, is that whenever you have a situation where you have x to a power over y to a power, you can combine them and put them into a fraction with that fraction raised to the same power. And so that's what we're going to do here. We're going to keep our 1/2 and we're going to say, all right, I've got 0.10 over 0.20, both of those to the b power. All right. Now we're going to simplify what's inside my parentheses here. So 0.1 over 0.2, that's 1/2. So we've got 1/2 equals 1/2 to the b. Now we have to ask ourselves, what does b have to be? What does the value of b have to be equal to? The only possibilities here that we're going to study in this class are 0, 1, and 2. Those are the only possibilities for now. When you get into advanced classes, you'll see that it gets more complex, of course. But for now, every single time, we're going to study reactions for which these orders, A or B, whatever, are 0, 1, or 2. And so if something's raised to the 0 power, remember, that turns it into 1. So that can't be it. B to the first power is equal, or sorry, 1/2 to the first power is equal to 1/2. That seems to work. If it were squared, this number over here would have to be 1/4. So we're going to say by inspection, that means we didn't do any real math. By inspection, b is equal to 1. All right? So that's some progress. So now we're going to come back up here and we're going to take experiment 1 and 3 this time. All right? Now we're going to do experiment 1 with experiment 3. All right? And that's going to help us isolate the order A. All right? So now we're going to plug in. Remember, our rate law, I'll just rewrite it real fast. Our generic rate law is CL2 to the A, O2 to the B. We now know what B is. We could go ahead and plug it in. We're not going to for now. So I've got a rate here of 1.8 times 10 to the minus 4 molar per minute equals the rate constant K times, what are my numbers? 0.1 and 0.1. A 0.10 to the B. Now, for experiment 3, the only change is this 0.2 over here in the CL2. So this is, again, 1.8 times 10 to the minus 4 molar per minute equals K times 0.20 to the A times 0.10 to the B. Same sneaky math trick, divide top by bottom. Ta-da! Notice that 0.1 to the B cancels, K cancels, molar per minute cancel, and oddly enough now we have 1.8 times 10 to the minus 4 over 1.8 times 10 to the minus 4. That's equal to 1. So we have 1 on the left-hand side, and that's equal to, and I'm going to skip over the little math trick I did earlier just to, because I think you guys have probably got it by now. All right, so that's that. 1 is equal to 1/2 to the A. Now, remember, A has to be 0, 1, or 2. Those are the only possibilities in this class. If it were 1, 1/2 to the 1 we saw a minute ago is 1/2. So that's not it. 2 would be 1/4. 0 is the only possibility here. So we know that this has to be 1/2 to the 0 power in order to get 1. Sometimes when you're rushing, people will think, oh, they see this 1 over here, and they're like, oh, A is 1. Yeah, it is. Slow down. Remember your algebra. Anything to the 0 power is 1. All right? So that means that by inspection, again, A is equal to 0. So now we can finally write our rate law. Rate is equal to K times, we had CL2 was A. So we can write it CL2 to the 0. I'll show you an easy way to simplify this in a second. Times O2, and we know that B is equal to 1. Now remember, right here, anything to the 0 power is 1. So we don't actually have to write the CL2. We can make this easier and write rate equals K times O2. And if you want to write the 1 here, you can. And if you don't write the 1, that's okay, because it's understood if you don't write it. All right, we are almost done with this problem. Believe it or not, there's more. So the thing we don't know yet is what's the value of my rate constant, right? So we don't have a value of the rate constant yet. So let's find that. Now, how are we going to do that? Well, all we have to do is plug in 1 of the experiments, any one of the three should give us a reasonable value. In an experimental situation, you'd plug them all three in and you do a bunch of math, average, whatever. But here we're just going to do one. So I'm going to take experiment 1, I'm going to plug it in, which, if you'll recall, that's 1.8 times 10 to the minus 4 molar per minute equals K times 0.10 to the first power. Okay, so now, and actually here, we need to be careful. So a lot of times when you write the brackets, you understand that the unit is molar, and so we frequently don't write it, but I'm going to write it explicitly here for reasons you're going to see in a second. So now to solve for K, this is straightforward algebra, I hope. So we're going to divide both sides by 0.10 molar. Cancel, cancel. So now over here, let's see, dividing by 0.1 is the same as multiplying by 10. So that's 1.8 times 10 to the minus 3. Now notice here your units get a little tricky. So you have molar and molar. Those cancel out. So you're left with per minute. For reasons that I don't entirely understand, the math people tell me that it's not right to write it this way. So what we normally do, that's all equal to K. We normally write this as 1.8 times 10 to the minus 3 minutes to the minus 1 is equal to K. And that is our final K value. So now we know the complete rate law is rate equals 1.8 times 10 to the minus 3 minutes to the minus 1 times the O2 concentration to the first power, right? And that is finally our overall rate law that we've determined from the experiment for this reaction. Now, one thing I want to point out, this K value is temperature dependent, okay? What that means is that if you change the temperature, you've got to do this experiment all over again because that K value is going to change. We'll look at the K value temperature dependence at a later point. For now, we just want to get down the math of doing these rate law equations, all right? But the temperature dependence of this K value becomes important later on. So even though we call it a rate constant, it's only constant if you don't change the temperature and if you don't change the reaction. So it's not really that constant of a constant, which is something you just have to keep in mind. Every single time you do the experiment at a different temperature, you got to reevaluate K. All right, thanks everyone.